What if we could teach quantum circuits to learn, just like neural networks? Welcome to Variational Quantum Circuits. In classical machine learning, we train models using parameters and gradients. But in quantum world, things work a bit differently and also a bit more powerfully. In this video, we'll explore how VQCs work, how to build them, how to train them, and why they might be the future of learning algorithms. Let's dive in. Today, we're going to discuss the topics variational quantum circuits and mathematical structure. What is a VQC? What are parameterized gates? Hybrid optimization loop? Structure of a VQC? Parameter shift rule? Use cases of VQC? Expressibility and trainability. The problem is barren plateau. Flowchart and code. Why VQCs are future of learning algorithms. Let's see about variational quantum circuits. They are quantum circuits with trainable parameters. They also combine quantum gates with classical optimizations. They are the core to modern quantum machine learning. Let's study about mathematical structure of VQC. We have an input which is classical data. We'll be taking input as classical data and then convert into quantum state with a parameter theta. Get off phi of theta comma x. Here theta is parameter set, which will have a wide range of parameters. And then we have a cost function, c of theta. It is cost specific objective. If we have energy objective, we'll have a different cost function. For loss objective, we'll have different cost function. Accordingly, we'll select a cost function. Now let's see what is VQC and common parameterized gates. A VQC is a quantum circuit that is structured as ket of phi of theta is equals to u of theta into initial basis state, where u of theta is unitarily composed of parameterized gates. What are common parameterized gates? These are rotation gates, either rotation around x or y or z. Here we'll be applying rotation on theta, which is a parameter which will change according to the cost. Why these gates? Why are we only using rotation gates? These provide continuous control over qubit state like a dial. They act like a dial. Small changes in theta will result in smooth changes in quantum state. Thereby, gradient-based learning is possible. The magic of PQCs lie in hybrid loop, which will help us build hybrid optimization loop. We'll see the set of steps which will help us build hybrid loop. Firstly, we'll have to set initial parameters, then run the circuit with these parameters, measure the results, thereby we'll calculate the cost. According to the cost, to minimize the cost, we'll update parameters classically. This loop continues till the cost function is minimized. Now let's study about the structure of VQC. We'll see the architecture flow. That is, firstly, we'll have data encoding. Here, we'll have the classical data which is encoded into quantum state. This brings classical data into quantum state. Then we have a variational layer which will be applied on the quantum state. We'll have a parameterized circuit with parameter theta. We'll apply this on quantum state to make it modified quantum state, which gives the model flexibility to adapt. And then measurement. From the here, we'll measure the output, extract meaningful outputs, thereby calculate cost. To minimize the cost, we'll update the weights accordingly. To train a variational quantum circuit, we need to optimize its parameters, just like in classical machine learning. But here's the catch. We can't use traditional backpropagation inside a quantum computer. Instead, we use a special trick called parameter shift rule. Let's say we want to compute the gradient of cost function with respect to gate parameter. The parameter shift rule tells us the derivative of expectation value with the respect to the parameter theta is equals to 1/2 times the difference between the expectation value of O evaluated at theta plus pi by 2 minus expectation of O evaluated at theta minus pi by 2. Here O is expectation value of observable O, theta is gate parameter. Use cases of VQC in quantum machine learning. VQCs are used in a variety of domains. In quantum classifiers to predict labels, in quantum GANs for generative tasks, in VQEs, variational quantum eigensolvers to find molecular ground states, in QAOA, quantum approximate optimization algorithm for combinatorial purposes. Let's see what is expressibility and trainability. A good variational quantum circuit should be expressive, that is, able to represent complex functions, and trainable, not to be stuck in flat regions. A VQC must be both expressive and trainable to perform well, but achieving this balance is very tricky. Expressibility measures how well a variational circuit can explore full Hilbert space. That means more layers will give more unitary complexity, resulting in higher expressibility. Higher expressibility is essential for capturing complex patterns or functions. A highly expressive circuit can represent a wide range of quantum states, which is vital for solving complex tasks like classification. But when it is highly expressible, we'll have a problem called barren plateau. Let's see what is barren plateau. A region of parameter space where gradient of cost function becomes exponentially small. Thereby, it results in the gradient vanishing. This makes the training impossible. Why does it happen? It can happen due to random initialization of deep circuits, too much entanglement too easily, global cost functions, example, expectation over all qubits. Let's see mathematical insight. Let cost function be c of theta. In barren plateau, the value of derivative of c with theta 1 will be inversely proportional to value of number of qubits. That means gradient vanishes as number of qubits increases. Now let's see solutions to avoid barren plateau. We have layer-wise training. Firstly, we'll train shallow subcircuits first and then freeze parameters. Gradually build up deep layers. This will avoid barren plateau. And then use local cost functions. Instead of global observables, we'll measure the localized properties first. This reduces gradient vanishing. Better answer. Avoid overly random parameterized circuits. Use problem-specific structures. Smart initialization. Initialize near identify or use pre-trained classical models to guide parameters. This will help us to avoid barren plateau. Let's see about the flowchart for implementation. Firstly, I have a classical input. I'll pass this classical input into a data encoding layer to convert them into quantum state. Further, I am applying a parameterized circuit on the quantum state to make it into a modified quantum state, which will have parameters. I am measuring the output and then I am calculating the cost. Further, accordingly, I am applying classical optimizer to update the weights and minimize the cost. This loop will go on till we'll get the minimum cost. Let's see code. In the code, I am importing necessary libraries. Firstly, PennyLane as QML, then NumPy. I am importing datasets, let's say make moves. This is for data preparation. I am importing chain and test split, standard scale. In the preparing dataset, I am taking 100 samples from this dataset and then applying standard scalar, splitting the data at the probability of 80% training and 20% testing data. I'm setting up the device as with 2 qubits. I'm setting up the quantum device with 2 qubits. Here, I'm applying the encoding layer, which will convert the classical data into quantum state with RY gate. We can apply any other gates also. And then in the variational layer, I'm applying Ry and C0 gate. Ry is for parameterized gate. It is as a parameterized gate. C0 is to entangle qubits. C0 will help to entangle the qubits. And then I'm applying a full circuit with encode and variational layer, both the functions simultaneously. Here I'm measuring the expectation value using Z operator. The output will be ranging from -1 to 1. As I'm applying Z, the output will be interpreted as prediction score. It will range from -1 to 1. But we need the output as a probability score that is 0 to 1. So I'm applying a prediction function which will result the output in 0 to 1. This will result the output like maps -1 to 1 to 0 to 1. And then in the cost function, I'm applying loss function which is mean squared error loss function. Mean squared error loss function I'm applying. And then I'm calculating, like I'm optimizing the weights accordingly with Adam optimizer with a step size 0.1. I'm calculating the loss for 100 epochs, printing the loss at every 10 epochs. I'm printing loss at every 10 epochs and then optimizing with Adam optimizer and then printing the accuracy at last. Let's see. At epoch 0, I have loss 41.95. And then Adam optimizer will optimize and the loss will be 26. Further it will be 20. And then if you see in this step, we have 21, which loss is increased in here. So it will try to backtrack again till the loss is same and then again we'll get loss of 20.27 at loss, which will be constant for several steps. So we'll calculate the accuracy here. We got an accuracy of 0.75, that is 75% accuracy with a loss of 0.2027. The loss will be 0.2027 and accuracy will be 75% in this code as we applied 100 epochs. The loss may decrease and test accuracy may increase with the more epochs, but here we are stopping as the loss is constant. Let's now discuss about why VQCs might be future of learning algorithms. VQCs harness unique quantum properties like superposition, entanglement, and interference, which may allow them to explore more complex data efficiently, represent functions that are classically hard to model, offer speedups in optimization, classification, and pattern recognition. And as quantum hardware improves, VQCs could outperform traditional neural networks in areas like quantum chemistry, financial modeling, drug discovery, high dimensional data classification. The key takeaways in this video are: what is a VQC? A variational quantum circuit is a quantum circuit with parameterized gates whose parameters are optimized via hybrid quantum classical loop to solve complex problems such as optimization, quantum chemistry, and machine learning. Then we discussed about mathematical structure, which is represented as follows. And then we have discussed about parameterized gates, gates like Ry, Rz, and Rs, where theta provides continuous control over qubit states, enabling circuit to adapt and learn. And then we've discussed about hybrid optimization loop. Quantum circuit prepares and measures states. Classical optimizers update parameters to minimize cost function. These loops iterate continuously until convergence. And then structure of VQC, data encoding layer, which maps classical data into quantum states, variational layer, trainable gates and entanglement, measurement, extract observable for cost evolution. Then parameter shift rule, a quantum native method to compute gradients by evaluating the circuit at shifted parameters. Then we have discussed about expressibility and trainability. Expressibility measures how well the circuit can represent complex states. Trainability involves how efficiently the circuit can be optimized. We have faced a problem, barren plateau, which where gradient vanishes exponentially in large circuits, making training difficult. Ongoing research focused on mitigating this. And then we've discussed about implementation of VQC. Then why VQCs might be future of learning algorithms. They combine the power of quantum computing, exponentially large Hilbert space with classically optimization's flexibility, enabling new kind of hybrid algorithms that could solve problems beyond classical reach, bridging the gap between current noisy quantum devices and practical applications in AI, chemistry, and optimizations. So we say that VQCs are not just an upgrade. They represent a new paradigm in how we think about learning itself.
Like and subscribe for more quantum computing videos.